Go ahead, Rodrigo.
Okay, guys. So we're recording class for those who are not here today, and just because we know that missing a class of chemistry is terrible, so um, you guys really need to check this out.
All right, thanks, Rodrigo. All right, so we started off by having people put the ones from the worksheet on the board. So we're going to go ahead and just put these up here. All of them look really good. So some of the easier ones, we had the NH4 plus was one that we did in class yesterday. So we've got the tricky part here is that we had to subtract an electron, and then the other part that students oftentimes miss here when we get to doing the quiz on this stuff, which will happen tomorrow, is they forget to put the brackets. There you go. And Henry's fixing his right now. Right, because you want people to look at it to know, well, this is a dot structure, but this is only right if you've added 3 electrons, or in the case of the NH4 plus, you've taken 1 electron away. All right, the other one that's CO2, and we figured out that there were 16 electrons to work with, and the 16 electrons forced us into a double bond situation. So which one was this similar to that we did in class?
Oh, you did similar.
It's similar to
Water? No.
no, not water.
Oh. SiS2.
Yeah, didn't SiS2 look the same as this? I guess we need a reminder. Right? SiS2 looks exactly the same. Well, gee, take a look at where silicon and carbon are in the periodic table. What do you notice? They're in the same family. Oh, and take a look at where oxygen and sulfur are.
Same family.
They're in the same family. So one of the things that you can start to maybe get a handle on is there's only how many nonmetals are there?
Not much.
Yeah, there's not too many. There's 10, 11 nonmetals. So the combinations of these things that you can use to get different structures isn't that large, right? So you end up if you can figure out the pattern of these things, a lot of times that'll help. Right? So again, the CO2 is very similar to the SiS2. All right, then we had, we got it back there, the SiF4. And here we had 32 electrons and we added them all up. Silicon in the middle, fluorines all around. Okay. Now, this is going to become a pretty similar, a pretty basic structure for us, right? Because I mean, you've got your central atom that has 8 around it, that stable octet that we're creating, and then there's all the fluorines that are attached to it that are have their number of electrons also. Okay, so that's going to be a pretty common structure for us. I guess we can do the PO4 then. This one's going to look a lot like this. Use a different color. PO4 3 minus. So if we add up all the electrons, how many did we get for that, Henry?
It would be 29. There it's 32.
Right, so it would be 29 electrons, but since it's a 3 minus, we add 3, so it would be 32 electrons. So you see that 32 electrons pop up again. So you can kind of, without even going through all the steps, you've got 32 electrons, same thing, 1 central atom, 4 things around it. So you can almost jump right to it. Now, of course, I've done way too many of these in my lifetime, so I can see these in my sleep. practically. So you guys want to, until you get to that point, you want to keep, just going through the rules. So you've got your, figure out how many electrons there are, put a pair in for each bond, complete the octets of the atoms connected to the central atom, and then look at the ones that are left over in that. Okay, and again, don't forget the brackets if it's an ion. All right, pretty good. Any problems with that one? Good. It's pretty simple. They'll get harder today, don't worry. All right, then we have our next one is the SF6, I guess. And so right away, this one gives us a little bit of anxiousness, but shouldn't be too bad. Again, we have the sulfur, and we're going to put the 6 fluorines around it. Total number of electrons. Who did this one? 48, Greg? So 48 electrons. And now, again, you can start to kind of work on some shortcuts, right? How many electrons are we going to put in? We're going to put a bond in for each. Each thing is attracted to the sulfur. But how many electrons are we going to put around each fluorine total, including the bonding pair? 8, yeah. So if we've got 8 and there's 6 of them, 6 times 8 is 48, right? This is why the math teachers told you know those multiplication things right away, right? So we know that if we complete the octets of the fluorines, that we're going to have no electrons left over. So oops, I think I did one too many there. All right, but we get something like that. Remember we did the one yesterday, the SF4, where we had 32 electrons, but then 2 left over for that lone pair there. Right? So we can have more than that octet around the central atom. Right? Good with that?
Can every element do that, or is it just like
good, yeah. Yeah, it's going to turn out that, and we'll see why in a little bit, that only elements in the 3rd period, so from sodium, magnesium across, well, I guess not the nonmetals, but the silicon, phosphorus, sulfur, chlorine, those elements and below can have expanded octets. So you can't do more than 8 electrons around carbon, boron, nitrogen, oxygen, fluorine. Okay, so you never want to do more around those. And let's see, there's one other one, the NH3. So NH3, we've got 5 with the nitrogen, 3 with the hydrogen, so we have 8 electrons to work with. Oops. Pair for each bond, and then our lone pair. And there. Good. So that was I don't know who did the NH3. Gary? Yeah. Or Waja. Good. All right. Nice. Good job. The other thing that was good here, like if I were grading these like it was your quiz, most everybody did a good job with these. Like I would give you full credit because you showed how many electrons you had to work with. You don't necessarily need to draw the little circles around these, right? It's not bad if you do it, but you don't have to. So those are all good. Yeah.
You have to identify the lone pair.
You mean circle the one there?
Yeah.
When you flip the page over, via CPR, that when we're actually going to figure out the shape of this, that lone pair is going to be really important. So with dot structures, no, it doesn't really matter too much. But when we're not going to stop here. This is kind of like a midway point, and then we're going to go on.
Okay.
So it will be important later to kind of highlight and know that that's there. All right. Any questions on that? Good. All right. Now, huh?
I have a question on the word problems.
Oh, okay. Yeah.
The arrangement for carbon dihydrogen.
Carbon. Which one?
C2H2.
Oh, good. What's that? Oh no, you can. Yeah, sure. Go ahead. Yeah. Yeah. So C2H2. Yeah. So this is going to be another issue. Basically, here what you have is carbon atoms are always going to be, the central atoms. What you're going to do in this case is you're going to put a carbon and a carbon, and then usually what you try to do is balance out the hydrogens. So you'd put an H on this carbon and an H on that carbon. Okay, so carbon atoms are never going to be, kind of at the end of a molecule. They're always going to be. Well, I shouldn't say never. I mean, it's. They're usually. I mean, you'll see as we start working with more of these things. And our next chapter is going to be on organic chemistry, which is going to have a lot of carbon compounds in it. So you'll see a lot of these. But you'll get used to these. But anytime you have something with more than one carbon atom in it, you usually have the carbon atoms bonded together, and then you kind of spread out the other things that are bonded to it. Right. So how many valence electrons will we have to work with here? Yeah, 4 from each carbon there, so it's 10 electrons to work with. Right. So we do a pair for each bond. That's 6. So we have 4 left over. Right? So we could do, well, the hydrogens are happy now, right? So we don't have to worry about those. So how do we make the carbons happy? Well, if I do that, are the carbons happy? No. So let's share. Now are the carbons happy? Yeah, well, the one on the right is happy, but the one on the left's not. All right, now are they happy? Yeah, now we can draw little circles and show that each carbon thinks that it has an octet around it. Right, so three pairs of electrons worth of electron density, is going to be a triple bond.
Like a really, really tight bond.
Excellent, good. That's the next thing I was going to say. What do you mean by tight?
Like they'd be really close. Strong.
It would be strong, so it would be a strong bond, and they would be close together, shorter, yeah. Yeah, so a single bond between 2 carbons is going to be the longest. If you put a double bond between 2 carbons, it gets a little bit shorter, and a triple bond will be even shorter. All right, that's good. Yeah, and we'll see more examples of that, with those. So whenever you see ones with more than one carbon, just put the carbons together, all right, and then put the hydrogens kind of around them. All right. That good? All right, now we're going to take a look at a couple of, well, at least one exception here. BH3. So what's going to happen with BH3? Well, it doesn't look like much of a problem to start with, right? But what happens pretty quick? Right, we only have 6 electrons. Boron has 3, and then 1 from each of the hydrogens gives us 6 total. So that's the best we can do. Right, that's the best we can do. Now, boron doesn't have a real high electronegativity anyway, so it works out all right. So you can have boron compounds. Beryllium is another one that can make actually covalent bonds, and it won't have 8 electrons around it. All right, so both of those can exist without having less than an octet, but most of the time you don't have. So that's one to kind of keep in mind. All right, the next one, however, is going to throw us for more of a...
Which two you say it was?
Oh, boron and beryllium. So B and Be. All right, now this one's going to throw us for a little more of a loop. Give this one a try. So see what you can come up with for the electron configuration for NO3 with a minus charge. NO3 with a minus charge. To record this. So let's take a look at this one now that we've had some chance to try it out. How many electrons do we have? All right, so 24 electrons to work with. So we put nitrogen, oxygen, oxygen, oxygen. And I like Francesco's idea of, just kind of getting it out of the way. We know it's an ion, so let's just go ahead and put a bracket around that. All right, so we put a pair in for each bond. We know we have to have those. Good host rule. And so we're all pretty good up to this point. I think we're probably even good with, all right, my central atom has fewer than an octet, so I need a double bond. All right, so I need to share some more of the electron density there. What should bother us here is, what?
It's like not symmetrical. Then
Yeah, it's not symmetrical, and why does this oxygen have to lose some of its electron density? This one doesn't have to. This one gets 6 electrons all by itself. Right? The other 2 do. It's only the one at the bottom here that has to share more electrons with the nitrogen. Well, that hardly seems fair.
Well, but would it matter? Like, would it matter which oxygen will
Okay,
share?
good. It does matter because each oxygen has an equal pull on the electron density, and this is where we want to be thinking about these electrons again as, not as individual particles, but as an electron density, right? So we're trying to. Each of these oxygens has an equal pull on that electron density that's in this ion, right? So it's not right that one of them, and it's not possible that one of them has a different amount of electron density associated with it than the other ones. Right? So what this creates is a situation called resonance. Now, this is one of the real pitfalls of dot structures. What I end up having to do is draw 3 separate pictures.
what's that called again?
Resonance. Okay, and each resonance structure is separated by a double arrow. And so you can see that, that it takes 3 pictures to really describe this, well. Right? So what we're showing is that double bond. Now, and this is another thing that we have to be careful of. If you're not a chemistry student and you look at this, even a beginning chemistry student, what do you think is happening to that double bond? It's moving around, right? So if you were to take a picture of this, what would you observe, or what properties would you be able to observe that could help you understand this better?
The weight property of the
Yeah, a little bit maybe. No. What property? We were just talking about it. What thing could we look at up here that could help us understand whether these were single or double bonds?
The length of the bond.
Excellent. Good. Bond length. Because if it's a double bond, what should happen to the bond length? It should be shorter. Right? So if that double bond were moving around, one of those bonds should be shorter. Right? So we take a picture of this with X-ray crystallography, and you know what we find out? The bonds are all exactly the same length. Excellent, Henry. Did you guys hear that? That was Henry that made that comment. Yeah. Each bond is a little bit shorter than a single bond, but not as short as a double bond. So what that tells us is that those 2 electrons worth of electron density, the extra electron density we have from those 2 electrons, gets spread out over all the bonds. Yeah, that's very good, Henry. That's very good. Now, that doesn't, it doesn't work real well with dot structures. Okay, later on we'll see something that shows it a little bit better. But yeah, that's a great thing. So by looking at the bond length, we can tell that these things are all actually the same bond length, which means that the electron density is spread out over all of them. So each of them is like 1 1/3 of a bond. All right, good. Let's see, what was the next one? Oh, and then here's another one that's going to be a little different, a little tricky. NO2. So why don't you go ahead and give NO2 a try and see what issue you run up against with NO2.